Exercise 1. Let's do it. Question number 1. A person runs with a speed u towards a bicycle moving away from it with speed v. The person approaches his image in the plane mirror fixed to the rear of the bicycle with a speed of. Oh, right. So approaches his image. So you mean the relative velocity of this guy as seen by his image, right? That's what you mean. So with respect to the mirror, this guy's velocity is just yeah, it's gonna be u minus v. So u minus v is also the negative of that, right? So v minus u, basically u minus v in the left direction. That's the velocity of the image. So that plus v, right? That would just be 2v minus u. So 2v minus u is the velocity of the image in the ground frame. And that's definitely not what you want. You want the velocity as seen by this guy. So it will be 2v minus u minus u. So that should be 2 times of v minus u is the velocity of the image as seen by the object, right? We just want the magnitude of that anyway. So it should be 2 times u minus v because u minus v is the positive version of v minus u. So there we go. I think D is the correct thing because they said velocity of approach is just the relative velocity of the of one object as seen by the other one, right? That's what is velocity of approach, I think. Okay, next. A beam of light strikes one mirror of a right angle mirror assembly at an angle of incidence 45 degrees. Okay. The right angle mirror assembly is rotated such that the angle of incidence becomes 60 degrees. Which of the following statements is correct about the emerging light beam? It will move through an angle of 15 degree with respect to the original emerging beam. You know what I mean? Like, okay, instead of rotating this mirror, you could just rotate the light beam, right? Because, yeah, I mean, we just care about the deviation between this guy and the final light beam, right? So rotating the mirror, if that makes it 60 degrees and so on, right? So your deviation will be different, and right, that's what's happening. Okay, we want it will move through an angle of 15 degree with respect to the original emerging beam, right? So you have to keep the original beam like that, like fixed, and then at 60 degrees, what should be the deviation? That's what you look for, right? Remove emerging beam. Right, that's what we look. Okay, so for 45 degrees, what's the deviation? So it's 45, 45 like that. That just means this angle is going to be 45, but that's 90, so it's also going to be 45. That just means, right, this is also 45. So it just goes opposite. It's 180 degrees is the deviation. What if it's going to be 60 degrees? If it is 60 degrees, what's the deviation? It's like this is 60. This thing will be 60. This will be 30. This will be 30 as well. No, sorry, 60 because 90, 60, 30, right? Yes. Then that means this is also going to be 60. So it went like that, and now it's coming out like that. Let's check what happened. First, it got deviated like this. So it got deviated by a 60-degree angle, and then it once again got deviated by this angle. And then what is this angle actually equal to? It's equal to this angle, I guess. Yeah, it was going like this, and now it, of course, I mean, this is the same thing as us, like that 60. So first it got deviated by 60 degrees, and then it got deviated by 180 degrees. That's so this as well is deviated by 180 degrees, which means, oh, yeah, it will emerge parallel to the original ray. Huh, that's amazing, right? So that means doesn't matter how you do this, right? It's gonna emerge the same direction. Is that really the? So what if I just did it for any angle theta? That would prove it, right? So if it's at some angle theta, let's say something like this. So this is our angle of incidence, I, and then this is how this ray goes. This is like that. Okay, it's gonna be I over here. This is going to be 90 minus I. So it's also then it's going to be I over here because yes. So it's going to be I over here, and also over here. So first, this guy got deviated by, oh, okay, I don't even need to do that. You can clearly see that these two are parallel because, yeah, this transversal puts the same angles over here, right? So, yeah, these results will be parallel. That's awesome. That means, yes, it will emerge parallel to the original emerging ray. So, second D. Third, two mirrors labeled L1 for left mirror and L2 for why L1? Okay. Okay, right mirror in the figure are parallel to each other. Okay, person standing 1 meter from the right mirror looks into his mirror and sees a series of images. Fine. The second nearest image seen in the right mirror is situated at, so at in this direction, right? Okay. So second nearest image. Of course, the nearest image is just at 2 meter away from this person, right? What about the second nearest image? So let's draw it up. You got this is like 1 meter. That's going to be 2 meters. You got these 2 meters. First image of this guy is going to be like 1 meter away from the mirror. Then this will get reflected over there. We don't care about that. The second will be when you have this being reflected into it. Yes. What would happen if I do that? I don't think that's gonna be a good thing to do. Yeah, it's gonna be too big a length to mirror. No, don't do that. Just do this thing. So it's gonna be 2 over here. So this is 2 plus 2 plus 1, which is 5. So it's gonna be 5 from here. Right. So first is at 1, second is at 5, I think. Does that make sense? It should. So it's how much away from the person? It's going to be 6 meters away from the person. So C. Fourth, the reflection surface of a plane mirror is vertical. A particle is projected in a vertical plane, which is also perpendicular to the mirror. Okay, the initial velocity of the particle is 10 meters per second and the angle of projection is 60 degrees. Okay, wait, what? Reflection surface is vertical, so something like this, right? So this plane, paper's plane is like horizontal plane. This thing is vertical. Okay. Oh, so that's what. So you know what? No, let's say that this plane. So this is our ground. That's our horizontal plane. This is so it's coming towards you. It's another vertical plane, and then this paper's plane is also a vertical plane, but not this one. It's perpendicular to that. Perpendicular to mirror, the initial velocity of the particle is 10 meters per second and the angle of projection. Right, it's like projectile motion, but it's mirrored over here. The point of projection is at distance 5 meters from the mirror. The particle moves towards the mirror just before the particle touches the mirror. The velocity of approach of the particle and its image is just this velocity. Yeah, okay, let's do it. So it's at what distance from the mirror? 5, and it's being shot off with 10 meters per second and angle of projection 60 degrees. That means horizontal velocity is 5, vertical is 5 square root 3. So in 1 second, it's gonna go over here, right? In 1 second, what does this velocity become? It's gonna become 5 square root 3 minus 10, right? So yeah, now it's 5 in this direction and 5 square root 3 minus 10 in this direction. Doesn't matter because in the end, this velocity is gonna be gone anyway, right? This guy is moving like this. Its horizontal component is what's getting mirrored. The vertical component stays the same, right? So like the relative velocity thing, this will cancel it up. So you just have this. So 2 times of that. 10 is the approach velocity. Yes. So fourth A. Fifth. A boy of height 1.5 meter with his eye level at 1.4 meter stands before a plane mirror of focal length, sorry, of length 0.75 meters. Okay. So boy's height is 1.5, eye level is 1.4. What is the question though? The height of the lower edge of the mirror above the floor is 0.8. I should draw this first of all. So this guy is 1.5. This might be like the 0.1. Yeah, meter. This is 1.4. This is where the eye level is. You got a mirror which is length 0.75. The height of the lower edge of the mirror is 0.8. So like this, and then 0.75. So that's more than 0.6. So it's gonna be somewhere. Oh, it's even more than 0.7. So here, somewhere like that. Yeah. Then the boy will see his full image. Well, it can't because this is too high, right? Thing is, this kind of thing should, so it should be 0.7. If this bottom edge was lower than 0.7 or equal to 0.7, it would have worked, but it's not. So he cannot see the full image. Well, he definitely can see his hair because, come on, it's quite above it. So yes, this can definitely happen. Sorry. Right. So boy will see his full image. No, the boy cannot see his feet. Yes, correct. The boy cannot see his hair. He can. The boy can see neither his hair nor. No, he can. So he can see the hair. C. C is the answer. Is this? Yeah, it must be correct. Let's just not check because these seem like easy, the easier kind of questions. Okay, two plane mirrors are inclined at 70 degrees. The ray incident on one mirror is at angle theta. Okay, after reflection falls on the second mirror and is reflected from there parallel to the first, theta is. So this angle is like 70 degrees. This is incident at an angle theta, and then it's reflected parallel. Okay, so maybe like this. Okay, this is actually theta. This will be theta, and because these are like parallel, what should happen is that this. Yeah. I mean, I get that. I'm getting the thing. It's symmetric. I get that. Still, I just go with the normal way of doing it. So it's gonna be 90 minus theta right here. So this plus, yeah, so 180 minus that. That's gonna be 20 plus theta is this angle, I guess. Yes, and then this should be parallel. This is also like 20 plus theta. And what about this? It's also 20 plus theta. So what should happen is that 40 plus 2 theta, that should be equal to 2 theta. Wait, what? That doesn't make any sense. It has to be parallel. This has to be happening, right? Is that correct? It must be, right? So that's 160. 180 minus that is 20. So you got 20 degrees, but you also need another theta so that you can fill the thing. 20 plus theta is over there. That's supposed to be 2 theta. Oh well. That's unexpected. You know these angles must be same. Reflected parallel. Well, this line is the same, right? So this must be the same thing as that. But that means 40 is equal to 0, which makes no sense. Where am I going wrong? Where am I going wrong with this? Oh, sorry. Parallel to the, what am I seeing? Parallel to the first mirror. Okay, so the thing is, these can never actually, oh, wait. So the deviation is kind of, you know what? Scrap that. We will actually figure out what the deviation is for any kind of angle. So if it's angle A and it's like falling at incident angle theta, then it does something like this. You got theta over there is 90 minus A, 90 minus theta over there. This will be 180 minus that. So 180 minus 90 is like 90. 90 plus theta and then minus A, right? So it's 90 plus theta minus A. In other words, 90 minus A plus theta. So this will be 90 minus A plus theta, but it's gonna go like that. So it's like this is also 90 minus A plus theta. So what's the deviation that this actually suffered? So first you have this thing, right? So it's just actually this thing. So it's going to be 180 minus 2 theta, and then it suffers this deviation, which is plus. So this is like 90 minus, so 90 plus theta minus A, right? So 2 times of that. It's going to be 180 minus 2A plus 2 theta. So wow, it's a constant deviation. It's 360 minus 2A, huh? So these guys always go with a constant deviation. In case it becomes 180 degrees, what should happen is that A should be 90 degrees. So only that angle actually gives a parallel, right? Okay, that's understandable. Fine. Now let's get to the question. They are saying A is 70 degrees, and after this happens, well, theta so sorry, this reflected ray is parallel to the first mirror, so it goes in this direction, huh? Okay, okay. So if it's parallel to this, then this angle must be A. Yes, but we know it's just right. This, what is this angle? That's kind of scary, you know. Oh, sorry, sorry. No, this angle must be A, right? Because clearly that must be the case. So what should happen is that this quantity 90 plus theta minus A, that should be equal to A. So that just means theta is equal to 2A minus 90. In this particular case, it's going to be 140 minus 90, which is 50. So it should be 50 degrees. This is a nice value, I think. I mean, okay, I'm not going to remember this in any way, but hey, whatever. It's like 360 minus 2A. Which question was that where you had the 90 degrees? So second question, right? So we just say del is equal to 360 minus 2A. A nice thing, we can just remember it. Seventh is two plane mirrors L1, so sorry, length L. Plane mirrors of length L. Okay, these, fine. Separated by distance L. What? Wait, I don't get it. What is this diagram for this? Two plane mirrors of length L separated by distance L, and a man at distance L from the connecting line of the mirrors as shown. Connecting line of the mirrors? It, okay, connecting line of the, huh. Oh, okay, okay. So you mean the line which both of these are lying on? Okay, okay. Now I understand this. Right. A man, M1 is walking in straight line at 2L parallel to the mirror at speed U. Then M2 at O will be able to see M1 for the total time. Oh, right. So yeah, for what parts of this length will you see it? So just draw a better diagram. So you are saying these are separated by length L, right? These two plane mirrors. Yes. So this distance between them must be L, even though you didn't actually, I mean, give that, but hey, whatever. So this thing is L. That's our first plane mirror. This thing is other plane mirror. Sorry, okay, this is our mirror. This is not a mirror. Then you got L over here, this screen. Right. This first observer is at L distance over here. Yes. Okay. And then this guy is at 2L away. And right, it's moving with velocity U. Where does it start off? So you didn't give us where it starts off, right? So we just say it's starting off from a very far away place. Right. So now, first of all, for what range can you actually see this? So you will have something like this. Okay, this angle is going to be 45 degrees. We can just see this. So it's going to be 45 degrees like that. Yes. So this is also 45 degrees. And then this is like 2L. That just means, ooh, nice. It's going to be 2L right here. And then you will have this angle. Right. So we know this angle must be, because, oh no, okay, so the tan of this angle is 2. Call this thing angle as theta. It's like this is 90 minus theta is going to be theta right here. So theta right here as well. What is this? Right, so this whole distance. Wait, why did I draw 2L like this? Okay, it's supposed to be like that, you know. Anyway, the thing is, let's just say, okay, this is our origin and then this is our x coordinate. So this point where it starts off, seeing it is at 2L plus L, so it's actually 3L. So starting off, just have 3L, and then the last x value you will have is, so this is theta, tan theta is just 2. Well, this is like 2L, so it's going to be 4L over here. But then this whole length is like 2L, so 2L plus 4L is going to be 6L. I know my diagram is not good, but it's enough to convey my understanding, right? So yes, let's draw a better diagram. Right. Yeah, right. So, okay, we messed up. We messed up really bad. Thing is, this angle is not 45 degrees. So bad diagrams sometimes do play a role in destroying everything, huh? Right. So once again, now what's tan of this angle going to be? Let's call this thing as theta. So we'll have this being theta, and then this will be 90 minus theta right there. So the angle of uh, you're not doing that. No, you're doing like this. Sorry, now everything's just messed up. This is how it should be. This angle is the same thing as that angle. And then what is this coordinate? That's what we look for, right? So, right, these all angles are like equal. And the tan of this angle is just 1 upon 2, right? So this thing is 2L. 2L times tan of that angle is going to be just L. So this thing is L, but then this was already L. So you start off at 2L in fact. Okay, for the final guy, what do you have? Tan of that angle is just 2, right? Because this is L and this, no, not 2. It's L upon 2 and then you got L. It's like 3 upon 2L. So that is just 3 upon 2. So 3 upon 2 times 2L is just 3L. Now, once again, just like before, L plus 3L. It's like 4L. So it's 2L and then you have 4L. So yeah, and then of course there are like 2 such intervals where this guy will be able to see it. So the length of the intervals combined is just going to be 4L. 4L upon this speed is the time for which it can see it. So 7th A. Let's go to 8th now. A point source of light S is placed in front of 2 large mirrors as shown. So S is a point source placed in front of 2 large mirrors. Which the following observers will see only one image of S. So they are like, okay, these observers will only see one image of S. Fine. Yes, understand this. Wait. Okay, which of these will see only one image? Why would that happen? Huh. That's S over here, and then it does form that image, and then it will be as if it's coming from there. Yes, that's understandable. And yeah, that will in fact be for all of it. Oh yeah. Okay, now I understand why A will not see that image. Right. So if we were like infinitely far away somewhere over here, we would see all kinds of images that this can form. But A actually won't see the image because so you have this S over here, right? It's somewhere over there. You got this it's like it's 30 degrees, like it's only 60. So this is 30, this is 30, somewhere over here, right? This is drawing. Oh, and that's 90 degrees over there. Is that for? So that's 60 degrees. Okay, whatever. Just deal with it. We draw a better diagram. This is 30 degrees. So that's our S over here. Now, what will happen is that this guy will have an image like this, right? And your A is over here. How is this actually having an image? All the rays appear to be coming from here. So you could just think of for all points on this plane, you will connect that point and this to form the ray that appears to be coming from this point, right? So the thing is, will we be able to find a point such that a ray finally gets to A? Actually, yeah, you will be able to get a point like that because that's 30 degrees right there. and now you can find a point by doing this thing. So yes, there is a point that actually works. So okay, A will see it. A will see this image, fine. What about the other image? So you will have this thing, and then there's going to be more than that because yeah. So will it see this image? I think yes, because okay, A is somewhere above it, right? Even though it is a very small height, it is a height. So you are still able to find a point such that a ray can appear to be coming from here. So that's, I mean, yeah, this is the ray that we will see. So bunch of rays that it will see. Yes. So A can see both. So A and C, these options are just incorrect. So what about C? What about the point C? It's similar to A except that it's on the other side. So see what happens to that guy. So C is somewhere over here, right? Then S is like this. That's 90 degrees. Oh yeah, so this guy has an image like that. The first image is like this thing. Will this actually have? No. The thing is, there's no point. So if the mirror was extended, this is the point from where rays will appear to become, right? I mean, okay, what I'm saying is, this will be the point on the mirror that would have reflected the ray such that it would appear to come from here. But there is no such point. The mirror is not here. It's just, yeah, like light cannot go for this point. So that means C cannot actually see the image of S in the horizontal mirror. So C is definitely a candidate. What about B? So B is somewhere over here. Well, once again, connecting this, you can definitely see this image. Okay, what about this guy? Well, we can still see that image. So B actually can see two images, might even see more images, but thing is only C can see one image, a single image. Yeah, that's our best choice. Okay, how do we prove that it will actually see a single image and not, so it's gonna be like multiple images over there. So I'll delete this stuff about B. Also this. Okay, that's our point C somewhere over there. So this is our first image. Let's just not think about this. And this guy is going to be somewhere over here. Yeah, right. It's in this angular region, and that's why I cannot see this image. Okay. You cannot see that image. Well, this image, does it act as an object for this whole mirror? Well, it doesn't, right? It doesn't. There's no way that rays can go into this. So no, it doesn't. What about this? Does this act as an image for this object? Well, I think it can. It can. So for example, for this point, if you want reflection on this point, you just join this line and then see. Yeah, so like it will actually happen. Okay, but you got a weird kind of angular range just like this happens. So its reflection is somewhere over here, but C can actually see that, right? No, it can't. No, it can't. Thing is, all of these points will reflect away like this. Remember, the rays are coming from this, I mean, at least they appear to come from this point. And then all of the time, this will be reflected like that. So, yeah, and then this is the critical ray. So if this was in this region, if C was in that region, it could see this point, but it cannot because it's not in that region. So C does see only a single image, right? That's nice. It's really nice. So B. So the 9th now. I wish there was a faster way that I could analyze this thing. The circular boundary of concave mirror subtends a cone of half angle theta at its center of curvature. Right. Cone. Okay. Circular boundary of the concave mirror. That's a circular boundary. So concave. It's not a cone of half. It's not a cone in the first place. It's something like a solid angle of a sphere, right? That's So concave mirror is a part of a sphere, and this will make sense. Okay, whatever. Oh, just the circle. No, okay, okay. Not the whole surface, just the circular boundary. So what they're saying is like in 3D, you will have this being a part of a sphere centered around this curvature point, center point, and then just this boundary, just this boundary of this mirror, not the whole surface, right? That's subtending a cone. Understandable. Okay. So what do I do with that? They are asking the minimum value of theta for which ray incident on this mirror parallel to the principal axis, so like that. Okay, any ray suffers reflection more than once. Huh? Reflection more than once. Oh, huh. Okay, okay. Now I understand what it's trying to say. So, parallel to that, huh? It's gonna pass through. Okay, it's not a mirror with a small aperture. That's just not correct. So theta can be a large value as well, right? So that whole thing of it passing through a focus, that is incorrect, really incorrect. If this was a parabola, it would have been correct, but it's not. It's a spherical mirror. It's not correct. So how do we do this? Think about it. You got this. Just cross here actually. So you got parallel rays, and then you want to reflect that. To reflect that, all you do is just form this thing, and then take this guy's reflection. All right, so it's gonna intersect over here actually. I mean, yeah. So whenever the next time this ray will intersect with the circle, it's going to be at the mirror image of this thing, taking this as the mirror, right? So taking the normal as the so-called mirror over here. Yes, that's what should happen. And what they're saying is that that should happen for at least a single. What if this actually does not happen? What's the minimum, sorry, what's the maximum theta such that this actually does not ever happen? Right, let's find that, you know. Yeah. So you are just taking the reflection of this point about that and seeing if that is actually over here, right? So, right, so for, wait a second. Okay, whatever, just got this thing. If you want this to be, okay, this is, instead of just talking about, you know, like the rays, we can just talk about the points themselves, right? So this point must lie on this arc, right? And then, okay. So yeah, okay, now I think I see what's the thing that we're actually looking for. So you got this circle, right? You have a segment of this basically. So this thing, yes. Now this is only to a certain x coordinate range. So yeah, something like this. Only, right. So only the points that, so only the points with x coordinates in this range will actually be reflected. Right. Yes. So for example, this point, so this ray, it will not be reflected. That's pretty obvious, right? So you just want a point in this arc, and you want that to be reflected such that it actually lands on this. That's crazy, right? So let's starting on what about this point? So this point just reflected. Wait, when you reflect a point on the circumference about this normal, so no, not that normal, like the normal joining these. Okay, that's not the thing. That's different. It's not a diameter. No, no. Only if this somehow works out to be perpendicular, only then would actually work. But it's not always perpendicular, right? Only then would this point actually be reflected over here. So a pass. through that. That's what you're saying. Oh, you are not reflecting the point. You are actually reflecting this whole ray, right? Ah, it's like an isogonal conjugate. Okay, okay. But not just about this point, you will have a changing point like that. Uh-oh, but then, this isn't good. Think about it, you just got some random ray and then you have this reflected about your origin. So just have this ray. These two distances are like, oh, it's lying on the angle bisector of these two rays, right? Huh. Okay, that's nice. That's pretty nice. What about this point? Oh, come on. How does this vary? That's all I'm asking. How does this vary? It should be somewhere. Okay, just think about it. Like, when is it not on this thing? What defines this point being on this? What about this x coordinate range thing? Is that a way of doing it? No, no. You also have to talk about this coordinate, which is definitely okay. That's not easy to do. When will this point be in that range? Oh wait a second. This. Oh, if that's on this arc, what should happen is that like this arc will actually subtend an angle less than this complete arc, right? Yeah, at least that condition should be satisfied so that this actually happens, right? Okay, that has to be satisfied, uh, right? And now this point we know is just like from the reflection of that, right? So a horizontal ray about this. So it's getting complicated. So if this angle is like theta, this angle is going to be theta as well. Understandable. And you are saying, well, this angle must be bigger than, sorry, smaller than the angle spent by this whole thing on this guy, right? So that should be less. Let's not use theta. Let's use alpha and also draw a better figure. This is some kind of geometry that they are doing. Once again, just a circle. You got this thing. You got this. Okay. If it has to happen, what should happen is like, okay, you got this, and then slightly. Yeah, this feels better. So if this is hitting at an angle of, let's say, alpha, right? This is also going to be at angle alpha, of course. That makes sense, right? Huh. We know that's the reflection of this. Wait, if we are reflecting the whole line, why even think about this point, right? Just think about the line itself. But isn't that okay? Maybe that's the best way to do it. This is so complicated. It's gonna hit somewhere over there. Okay, fine. But when will this point lie on that line? That will happen when this arc is smaller than this complete arc. That's it. That's what we have to do. Right. Now I have the complete condition. So before my condition was like this arc must be smaller than this arc. But now my condition is this arc must be smaller than this complete arc. Right. That's what I want. That's really what I want, huh? Okay. Okay. Now think about it. How do I do that? How do I measure the thing? So let's not think about this. Let's just think about a point, right? So this point is mapped to that point somehow. That would make sense, I guess. Right. Think about it. Well, this is vertical. That's pretty important, I guess. So this angle is theta. That's nice. Okay. What's the angle subtended by this guy? In case, so let's just say this is not angle alpha. Instead, we'll say, actually, no, that is correct. If that is angle alpha, then this is also going to be alpha anyway. Yes. Yeah, I mean, this whole thing is a pretty angle alpha over here. That's okay. So alpha in this case just belongs to negative theta to theta. That makes sense, right? Yes. So think about it. You got alpha over here. Well, yeah, that's what's happening, right? This is alpha, is alpha, and then you reflect, so you get this new line, and then it's hitting over here. What is this complete arc? Subtending. Actually, not this arc. Uh, yeah, well, that arc. You know what? No, let's just skip the thing and go to this arc. So this arc should subtend a less angle than this complete thing. What is this arc actually subtending? Well, this is vertical, right? Yeah, that's important. This is actually vertical. So that's 90 degrees over here, and that is alpha, right? This is alpha. You can figure out what this angle is from here, right? Yeah. Wait. That's alpha, and this is also alpha. And oh yeah, this is not vertical. This is not vertical. This is vertical, and that's just some random angle. Yes. So this complete thing would be theta, not just that. We know this is going to be 2 alpha over there, and you got this. Oh hey, look, an isosceles triangle. This is alpha. This is also like alpha. That's 2 alpha. So what is this angle going to be? That's going to be pi minus 3 alpha. So what should happen is that pi minus 3 alpha should be less than theta. Yes, that's our condition for the reflected angle to be on the mirror, so that you have a second reflection. And then alpha just belongs, so there should be at least 1 alpha such that this happens, right? Exactly. So for some alpha, this should happen. So for some alpha, 3 alpha is bigger than pi minus theta. So for some alpha, alpha is bigger than pi minus theta upon 3. But we know that actually alpha just lies in the range of negative theta to theta. So we know alpha is less than theta. So there we go. That's the thing. So what should happen is that 3 is like bigger than or equal to, but hey, whatever. The critical condition is what we're looking for. So 3 theta is bigger than or equal to pi minus theta. So 4 theta is bigger than or equal to pi. So theta must be bigger than equal to pi upon 4. So that's 45 degrees. So for 45 degrees, you have the second reflection happening the first time, which is of course at the maximum alpha. That's when this whole thing, so pi minus 3 alpha thing will be the least. So it's definitely at the highest alpha. Right. Now we have a good proof of this. So there we go. Pi upon 4, which is 45 degrees is the thing. So C. 10th. That's some solid geometry. I don't think this would ask. I know there's a more guesswork kind of way of doing it. So just figure out when the critical condition might happen. So just guess basically. But I like to do it with full rigor. 10th. An object O is placed in front of a small plane mirror M1 and a large convex mirror M2 of focal length F. The distance between O and M1 is X. O is placed in front of a small plane mirror M1. No figure given. And a large convex mirror M2 of focal length F is between O and M1. And the distance between M1 and M2 is Y. Images of O formed by M1 and M2 coincide. The value of F is, that's a pretty vague question, because I could place it in multiple different ways, right? I could place it like this. You got the M1 mirror over here, M2 over here. Then the only way that these could actually coincide would be if these are at the same point. Which, yeah, like you should have specified what's happening. So there's one other way which doesn't have this image at point scenario, which is you just have M1 over here and then M2 over here. Right. That's when this will happen. And then of course it's the other stupid way of thinking about it. So you got M1 and M2, which makes no sense. they should have given us that these are having the same axis or something like that, right? Or give us a diagram. This is why would we do that? Okay, this is the thing that we're actually dealing with. So you are saying, what you are saying is M1 is a plane mirror. Wait, a small plane mirror M1 and a large convex mirror M2 of focal length F. Why should it be large? Oh, so I think they're talking about something like this, you know. So you got this object, you have M1, so a small mirror, and then you have a larger mirror with less curvature, of course, and yeah, so M2 like this. So then it will be possible for it to for both of them to actually form images. Okay, so then these coincide. The value of F is right. So let's just say this is the actual optic center, right? So optic pole. Yes, this is our origin. O is not the origin, right? So we know this is Y. This is distance like Y. That's X over here. So at the X coordinate of negative X, negative Y. So like just have U is equal to negative X, negative Y, and then for M1 the image will be at so M1's coordinate is just negative X, so that minus Y. Sorry, it's negative Y. So minus X is the coordinate as in the M1. So plus that, plus X, right? And then plus X minus Y, that's the coordinate. So this will have plus X minus Y as the coordinate, right? Yes. Which we'll call as like, I don't know, V1 is equal to plus X minus Y. That's the coordinate as seen by this one. So what about V as seen? So yeah, that thing. Just have 1 upon V is equal to negative 1 upon U, which is just 1 upon X plus Y plus 1 upon F. This is like negative 1 upon F. Right. So if these are coinciding, then what should happen is that V1 should be the same thing as V2. So there we go. 1 upon X minus Y is equal to 1 upon X plus Y minus 1 upon F. So 1 upon F is equal to, that's what you want to find, right? The value of F is. So this minus that. So 1 upon X plus Y minus of that is like Y minus X. It's going to be equal to 2Y upon Y minus X squared, which is, oh, that's 1 upon F. F is just 2Y upon Y minus X squared. Sorry, F is Y squared plus X squared upon 2. What am I doing today? So, that's unexpected. Convex mirror. Does it even matter in the end? Oh, come on. Why is this X squared minus Y? That doesn't make any sense. Minus, that's like plus Y minus X over there. Just, it should be 2Y upon Y squared minus X squared, but that's not there. Okay, I'll just have to go for A because that's the most sensible one here. Although this should be the thing. I don't get it. Why would it be the thing? So you are seeing like X is bigger than Y. Oh, and by the way, it's like this. Doesn't really matter in the end. So X is bigger than Y, you're forming like some kind of virtual object when you reflect that. Okay, that's pretty obvious. Virtual image. And then for this guy, you're gonna reflect that, and then it's gonna form somewhere over here. Hey, this doesn't make any sense, right? No, that just doesn't. No, actually, yeah, it will form a virtual object, the virtual image as well. So, could happen. Definitely could happen. Is this not correct to say that V1 is just that? Yeah, it's got to be negative by plus x. And then putting that in there, should get this thing. So, oh, why is there a negative over here? Okay, that's where everything went wrong. It should be, okay, so negative of that. That's why x minus y squared. So, A is the way to go, 10th A. So to 11th. A point source is situated at distance x is less than f from the pole of a concave mirror of focal length f. At time equal to 0, the point source starts moving away from the mirror with constant velocity. Which of the following graph best represents the best variation of image distance with with the distance x between the poles of the mirror and the source. Point source distance from the pole is given as x. Focal length of the mirror is f. Okay. So away from the mirror, the constant velocity. Oh, away from the mirror. Fine, fine, fine. So the following graph below represents the best variation of the image distance. Right. Okay. So first it's first of all it's before the focal length, right? So it when it starts going away, right? Object is just virtual at that point, right? It's a concave mirror and everything. Doesn't matter in the end. Right, so it's a virtual object. It just means your V is, oh, so you want mod V, huh? Fine, we'll just do V first and then mod V. So your okay, whatever, just do mod V directly. So this is your mod V. You know, your V is first of all positive, and then right, it starts off, and then it's like it's a max not value, right? Some value till there. Now at focus is gonna go up, so it's asymptotic at that point. You know, your V is now going to switch to negative, but we are talking about mod V, so it's still positive and still asymptotic. Okay, then till the center of curvature, your V will keep on decreasing. Yes. Yeah, it will keep on, and then it will start to keep on decreasing. In fact, yeah, it will just decrease. It won't ever increase back. Right? So there we go. It goes like that. So that's A for sure. So 11th A. So to 12th. Distance of a real object from the focus of convex mirror of radius of curvature A is B. Okay. Convex mirror, huh? Then the distance of the image from the focus is. So from the focus, it's B. Oh, that's fine. So radius of curvature A, your focal length is just A upon 2, and it's positive, by the way. So your focal length is positive. And then your U is just going to be, so it was B, so negative B as seen by the focus, but the focus is like A upon 2 up, right? So A upon 2 additional x value, you just have to add this, like A upon 2 minus B. Okay, so the distance of the image from the focus is, just use the formula. So like 1 upon V is equal to negative 1 upon U, which is, yeah, well, negative of this thing. It's supposed to be a real object, huh? Does it even matter? Okay, just 1 upon D minus A upon 2. So a negative 1 upon U. And then you got plus 1 upon F, which is just 1 upon this guy. Yep. Okay. This is going to be B upon A upon 2, which is called as F. F upon B minus F. Yes. Yeah. Now that you have this, we just want the B thing. B is just like F times B minus F upon B. But that's not going to stop. We actually want the thing as seen by the focus. Yes. So according to focus, its x coordinate is just that minus this guy's coordinate, which is now f, and that's why b minus f is what we look for. So this thing minus f, yes. Okay. So like f times of b minus f upon b, and that minus 1. So this will be f times of negative f upon b, which is negative f squared upon b. Yes. And now negative f is like a squared upon 4. So negative a squared upon 4b. Right. But you just want the actual magnitude. So a squared upon 4b. There we go. Wait, is that b or 1 upon b? No, that's actually b, not 1 upon b. So there we go. Negative a squared upon 4b. So 12c. Okay, let's go to 13. A concave mirror is used to form image of the sun on a white screen if the lower half of the mirror were to covered with an opaque card. Okay, the effect lower half was to cover with the card. Okay, the effect on the image of the screen would be. Oh right, so the thing is like the intensity will become half of what it should have been. Yes, but it's still at the same place actually. So the effect of the image, right? So to make the image less bright than before, make the upper half of the image disappear. No, that's just not correct. It doesn't happen like that. Make the lower half of the image disappear. No. So right, 13b is the most sensible one. 14. If luminous point object is moving along the principal axis of a concave mirror of focal length 12 centimeter towards it, when its distance from mirror is 20 centimeter from, okay, its velocity is 4 centimeter per second. The velocity of the image is 100%, and that instant is. Focal length is given, okay, along the principal axis of the concave mirror, right? Distance from the mirror is 20 centimeters, so u is just negative 20. Your focal length for, it's a concave mirror, right? So it's negative 12. Its velocity is, so our du upon dt thing, right? That's just 4. The velocity of the image, so yeah, positive 4, right? So sign convention wise, it's velocity of the image in centimeter per second at that instant is, so basically I'm banking of velocity. Yes. Okay. Once again, just pretty much the same things like negative 1 upon v square dv upon dt, then negative 1 upon u square dv upon dt is equal to 0. So really like dv upon dt is just equal to negative v squared upon u squared times du upon dt, which is, so hey, we don't know what v is, right? So 1 upon v is equal to negative 1 upon u, which is like 1 upon 20, plus 1 upon f, which is like minus 1 upon 12. It's going to be what? Well, 1 upon 4, 1 upon 5 minus 1 upon 3, right? It's like 3 minus 5 is just negative 2 upon 15. So that's going to be negative 1 upon 30. Yes. So v is just negative 30. Yes, that's correct. That's correct. Okay. So now we know what v is. We can do it. So it's like 3 upon 2, but that's like squared. So negative 9. Negative 9 of this velocity. So yeah, it's going to be negative 36. Right? Sorry, what am I doing? 3 upon 2, negative 9 upon 4 of this velocity. So it's going to be negative 9, right? Which is just 9 centimeter per second. Yes. Towards the mirror, of course. Because v is, no. It's v is negative. I thought it would be positive. Okay, if it's negative, then it's away from the mirror. Because it's already negative and it's becoming more negative. So away from the mirror. So 9 away from the mirror. 14c. 15. Corrects it related to the motion of the object and its image in the case of mirrors. Object and image always move along the normal with respect to mirror in the opposite direction. Move along the normal. No. They also have a y-coordinate velocity. Oh wait, in case of mirrors, but oh, you didn't say it's convex or concave, right? So no, this is wrong. Always move normal with respect to the mirror in the opposite type. No, this is not correct. Only in the case of convex mirror, it may happen that the object and its image move in the same direction. No, wait. You also have a virtual image, right? Wait. So virtual image by concave mirror. So as you, wait, what? So negative b upon u squared of thing. So if your du upon dt is right, it's always negative. Your dv upon dt is always negative of whatever sign your du upon dt has. So what is this saying? Yeah, okay. In that case, like in all cases, it's moving in the opposite direction. So what are we saying? Yeah, only case of concave mirror it may happen. They will never move in the same direction. That's what I'm saying, right? Isn't that weird though? They will never move in the same direction. Huh. Yeah, whatever. Okay, only in case of plane mirrors, object and its image move in the opposite direction. No, that's just wrong. Okay, that's just really wrong. We want to choose the correct statements. So A is also wrong. Along the normal with respect to mirror in opposite. No. That's they also have a y velocity. Only in the case of convex mirror, it may happen the object and image move in the same. Are we talking about point object or something? No, okay, so B and C are just really wrong. They will never move in the same direction, right? Because 1 upon B plus 1 upon B plus 1 upon F for all kinds of mirrors. Plane mirror, concave mirror, convex, whatever. Right? And because of that, just negative V square upon U square times T U upon dt. That's dV upon dt. So dV upon dt is always like it carries a negative of what the du upon dt should be. It just means it will always be opposite to du upon dt. So it's not possible. It's never possible for these two in the same direction. I don't get it, man. All of these are wrong. I mean, D is definitely wrong. It's only in the case of that's not correct. I think A might be correct, but then they are missing the y direction velocity. But hey, whatever. If nothing works, you have to choose something sensible. In the figure shown, the angle made by the light ray with normal in the medium of refractive index 1 is. Okay. The medium. Of course, I mean, you just know like n sine of alpha or theta or whatever. That's constant. So at 1, something like, okay, 1 sine of theta is equal to square root of 3 sine of 30 degrees, which is just square root of 3 upon 2. So sine theta is going to be, wait, what? This makes no sense. It will not go to the thing. Oh, wait, what? Huh? But clearly n sine theta must be constant. That's what we always do. So then, like what? That's where 3 upon, it's going to be 3 upon 2, but then sine theta can never be 3 upon 2. That means it just got reflected before even entering this, right? Yeah, that's what it means. Yeah, it never entered it. So D, how do I answer this now? That doesn't make any sense. This just doesn't make any sense. It's never going to enter it. So what angle are you talking about? So, first of all, in fact, it's not even going to do it. What? Okay, it might do it. So 3 upon 2 and then that upon square root. So 3 upon 2 square root 2 can happen, I guess. It's like square root of 9. No. Do it for this. Oh, it's gonna get reflected the first time itself. Huh? Yeah, it's total internal reflection. So it goes from a denser to a rarer medium, but it actually, I mean, it cannot have a proper angle. So it's just reflected. Boom. Because Wait, yeah, I mean like this has n sine theta equal to 3 upon 2, and then this will have like square root 2 as n, so sine theta will, so for this guy, so for the first reflection, just have sine theta is equal to 3 upon 2 square root 2, which is like square root of 9 upon 8, but that's bigger than 1, so sine theta cannot be possible, right? So this just gets reflected the first time itself. And I don't know what you mean by its angle in the refractive index of 1. That's not going to happen. So D, 16th D. It's none of these things. The correct answer should be it is not correct. It just never happens. Okay, bottom face of the glass cube is silvered as shown. A ray of light incident on the top face of the cube as shown. What? Bottom face of the glass cube is silvered as shown. Okay, this glass cube, okay, it has bottom face. Ray of light incident on top face as shown. Find the deviation. Once again, glass has a refractive index of 3 upon 2, right? Yeah. Find the deviation of a ray when it comes out of the glass cube. Oh, right. Oh, it's going to be a long question. First of all, figure out that index. What's this? It's just silver, and then just like this. Oh, mu equal to 2. They gave us the thing. Fine. So it's 2. What we had just got like 2 sine of theta is equal to that's just 1 probably. So 1 sine of, yes, like 1 upon square root 2. So sine inverse of 1 upon 2 square root 2, which doesn't make any sense. We don't know what that is. We don't know what that is. Some angle. Okay. Maybe we don't even need that, you know. So think about it. You got this. Got this slab, and then you just have. Thinking of something. Okay, whatever. So it goes like that. First of all, at some theta, we know what its theta is, but we'll ignore that. That's 45 degrees right there. And then this will be the same thing as theta. So like this is also the same thing as theta, right? So what about this, guys? This 90 minus theta right there. This is 90 minus theta, and then it's gonna. Wait, what? But that's reflecting a different thing if it's 90 minus theta. Oh yeah. Hey, it's going from denser to rarer medium, right? And then we know like sine of theta is just 1 upon 2 square root 2 is like square root of 1 upon 8. So yeah, sine of that angle, so that will just be square root of 7 upon 8, right? And then that times this guy's index, which is 2, that's equal to 1 times sine of whatever the sine is, like sine theta. Yes, sine theta 2 is like 5, whatever. So look at this thing. Oh god, square root of 7 upon 2. Yeah, as I expected. This is going to do total internal reflection. So it's gonna go like this, right? It's gonna, and you know, just like the previous case we did. So look at this, it's 90 degree. We know it's gonna go back parallel, and then once that happens, it just goes like this with 45 degree refraction angle, and that's it. It just comes out back parallel. So it's like 180 degrees is the yeah, deviation. So 17C. Huh. Yeah, that's nice. So 18th. A ray of light travels from an optical denser medium to a rarer medium. The critical angle for the two media is C. Okay. The maximum possible deviation of the refracted light can be. Oh yeah. Okay. Maximum deviation of the refracted light. So I know it's gonna be like a critical condition or whatever, but still, just do it with complete rigor. So you got some kind of incidence, and then you got yeah, this rarer medium. It's gonna be some kind of refraction angle, and the deviation is of course just r minus I. So r minus I is what we want to maximize, and our constraint is just that. Well, this guy's refractive index, so the rarer one has. Oh, that's not given. Critical angle is given though, so you can use that fact, I guess. Yeah. So what does that mean? Sine of the critical angle is of course just 1 upon the index of the tensor medium, right? Uh, or you could just say, okay, index of the rarer medium with respect to the denser medium. That's what this will be. So then just have sine C, right? So this medium with respect to that, of course. Then you just got sine I upon sine R is equal to the index of this rarer medium with respect to denser medium, which is, guess what, sine C, right? So that just means this is our constraint, right? So sine I minus sine C times sine R is equal to 0, and we want to maximize this function. Yeah, isn't there some easier way of doing this though? Uh, huh. We will say, okay, like R is equal to I plus delta, and we'll see what we get from that. So doing that, just get like, it's not 0. Actually, it is. It's 0. Yeah. So this is our delta. I want to maximize delta. Let's just put R is equal to I plus delta and see what we get. Sine I minus sine C times sine of I plus delta, which is sine I cosine delta plus cosine I sine delta is equal to 0 or something. So we want to maximize delta, but how is this going to work? We got this got like all of this trigonometry. It won't. It won't work. You will have to figure out something else. You will have to use the thing. You will have to use Lagrangian multiplier method to get this done. So just do it. Our function that we will consider is just r plus I minus some multiplier. You got sine I minus sine C sine R, and then of course you just want to not 0. You just want to maximize this function. So first take a partial derivative with respect to R. Let's say so you got 1 minus alpha sine C minus plus alpha sine C cosine R. Well, that must be 0. And take a partial derivative with respect to I, just means minus 1. Minus alpha cosine I must be equal to 0. So these conditions must be satisfied, of course. So, okay, like cosine I is just equal to negative 1 upon alpha. Nice, I guess. You know, like, okay, this is just useless unless you actually have a good condition. So just eliminate alpha from here, right? So alpha is equal to negative 1 upon sine C cosine R, but it's also equal to negative 1 upon cosine I. So guess what? These must be the same. Yeah, these must be the same. Or we just do 1 upon alpha over there and stuff. Hey, you get the idea, right? What must happen is like sine C cosine R must be equal to cosine I. Oh, huh. Okay, but we know that sine. Oh wow. Oh, but we already have this constraint that sine C sine R is equal to sine I. Guess what? We could just square this. We could just square both of these and add them up. It would be 1 is equal to sine squared C. Boom. Wait, what? That is really wrong. Yes, something went wrong. What is this? That's not correct. But this. Huh? Science is a constant, right? Where could I possibly go wrong over here? These are, of course, I and R that we have to deal with. But then this makes no sense. How would that happen? But that's what it's. Unless. No, okay, alpha cannot be 0. That would be so stupid of me to do. Right? Yeah. 1 is alpha cosine I. Yeah, you take a partial derivative with I and guess that. That's what you got. Okay. No, this must be correct. This just must be correct. Yes. Yes, R is I is delta. That's what you want to maximize. So to do that, you just do this thing and then boom, just take a derivative. 1 That's plus alpha sine C cosine R, and then you got other stuff. So minus 1, then minus alpha cosine I. You just want to eliminate alpha first of all, like 1 1. Yeah, plus 1, and then you got plus. Right, so from here you can clearly see that sine C cosine R must be equal to cosine I. Right, this is our condition. But then we know that sine C sine R is equal to sine I as well. But how does it make sense? No, it just doesn't make sense. Why would that happen? Wait, this is not making any sense. Like, but it clearly must be cosine. So, what went wrong? Just what went wrong? You are saying there is no maximum value? Is that what you are saying? There is no maximum value? Then just find out what maximum value of I will, yeah, so just gotta have I being pi, yeah, sorry, pi upon 2, and that will do it. Because turns out there is no such like value where it becomes maximum as a function. You just have to go with the fact that, right, so it's gonna be at the critical conditions, that is either when I is equal to 0, which okay, that's not correct because you only have negative numbers in the range as well. So it should be only at minus pi upon 2 and pi upon 2, which both are the pretty much the same thing, right? Yeah, so that's it. At the critical conditions on maximum deviation, which is to be expected, right? So all this stuff just gives us that information. I thought this was somehow incorrect, but no, it's giving us the same thing, that there is actually no such local maxima. No, it's going to be just cut off at pi upon 2. That's why you don't have this happening, right? That's what's happening. Yeah. So there we go. It should be like the deviation should just be but this critical angle. And now it's going like 90 degrees. So clearly 90 minus critical angle, that's our maximum possible deviation. So D is the way to go. 19th. Microscope is focused on a point object and then its objective is raised through a height of 2 centimeter. Okay, if a glass slab of refractive index something is placed, what? Microscope is focused on a point object. And then its objective is raised through a height of so what does it mean when a microscope is focused on? What kind of microscope is like a compound microscope or simple microscope? It's objective. That probably means it's a compound microscope. Yeah. So what does it mean when it's like focused at that point? Yeah, right. So it's like forming a wedge at infinity for sure. And so the other, you just have an objective over here and eyepiece. What is eye over here? This is forming image at infinity, of course. What's happening is like this guy is forming an image over here, so that this angle is now bigger than what it usually would be, right? Okay, that's it. And then it's like just a simple microscope. Yes. Okay, now you are saying if a glass slab of refractive index 1.5 is placed over the point object such that it is focused again. Placed over this point object. The thickness of the glass slab is what? I don't get what you mean. Over the point object. Okay, it's called a glass slab now. Such that it is focused again. What do you mean? I don't understand what you want to say. It is focused again. Oh, okay. First, you actually raise its objective to. So when I think when it says height, it actually means length, right? So even though we take it as horizontal in this setup, actually the microscope is actually like it's vertical, right? So object is raised to a height of 2, so it goes like this. It's changed by 2 meters. Yeah, that's what's happening. Okay, and then oh, but this guy's focal point didn't change, so it still should just form an image over here. Yes. Oh, so you're right. It's like that condition where this, okay, this is forming image over here first, and then it's moved, and now it should once again form image over here. For that, you put a glass slab. Yeah, thickness of a glass slab is, so it's so it moves by 2 centimeters. Sorry. Okay, and now you're gonna find the thickness of the glass slab. All we know is like, okay, the focal length of this thing is constant. Yes, so 1 upon b minus 1 upon u is constant. So whatever this distance might be, okay, plus, so 1 upon that distance, and plus 1 upon this distance, right? Yeah. Oof. It's kind of complicated, isn't it? It's moved back by 1.5. You don't give me the focal length. What do I do now? They just raised by 2. How does it make sense? Okay, now what? Without the focal length, how am I supposed to solve this? I don't get it. So, raised to a height of, yeah, without focus, it's just, so without the focal length, it's not easy to solve this. Okay, what does the glass slab do? It just shifts, right? It just shifts the whole thing. So your v minus u thing, yeah, that will be shifted by the thickness times 1 minus 1 upon u, which is like, okay, what was this, the thickness, and then 1 minus 1 upon mu is just, so if it is 1.5, so it's 2/3, of course. So t upon 3 is how much it got shifted, right? Of course, it's towards the right. Yes, think about it. You got this glass slab. You have these rays. Now these are gonna like converge because, yeah, because like this is a denser medium, so towards normal, and then it's gonna diverge back again. So it did shift. Yes, yeah, that makes sense. Towards the right. So now it shifted over here. Okay, so it basically like trying to decrease this thing. Wait, I think what's happening is like not the objective, the whole setup is now shifted. I think that's what's happening. Is that correct? I don't know. Just the objective is raised. But does that raise the eyepiece or not? I think it should. I think it should also, because only then can you actually solve this question. Without the focal length, and oh god, it's just so hard to do it. Unless you make some kind of assumption. If you don't know, what assumption could I make? So this should be equal to 2 meters, sorry, 2 centimeters. If your eyepiece is also shifted. I don't know how to solve this, so I'm just thinking about what went wrong while writing this question for them. So probably they forgot to say that the eyepiece also moves with it or something. Does it in real life move with the object? I don't think so. Your tube length decreases, and that's what changes the magnification. Yeah. Oh, also, yeah, like you're okay. Whatever. This is the thing. So it just tells like, okay, the thickness must have been like 6 meters. Sorry, 6 centimeters. Yeah. So A. I don't know. I think it's very incorrect to do this, but whatever. 20. A cubical block of glass of refractive index N1 is in contact with the surface of of water of refractive index n2. A beam of light is incident on the vertical face of the block. After refraction, a total internal reflection at the base and refraction on the opposite vertical face. The ray emerges out an angle theta. The value of theta is given by. Okay, fine. Right, so, wait a second. Wait a second. Isn't that just, huh? It's very weird. Wait, what? Wait, okay, last time when I said 180 degrees in that question, where was it? Where was it? Yeah, over here, right? So, oh yeah, in this case it was justified because this was doing TIR over here, right? In this case, I can't do that. Yeah, that would be really wrong for me. But we know that these two angles must be the same. So like it's just taking the mirror image, and then this is also kind of like a mirror image because it doesn't matter what the height actually is or the width actually is. It's just the surfaces that matter, right? So yeah, well according to that, this angle is the same thing as that angle. So total internal reflection at the base and refraction of the opposite vertical. Right. So, oh, okay. You want an inequality. That's understandable. Right. So, like this angle must be bigger than the critical angle, which is just sine inverse of n1. Yes. So, let's call this thing, I don't know, theta. So, this angle will be theta. Then this angle is also theta. Yeah. So, this thing is just 90 minus theta. So, yeah. And this is like air. Cool. Oh wait, okay, they already used theta. This is called alpha. So alpha is more than sine inverse of n2 upon n1. Sorry, it should be n1 upon n2 because it's no, that's denser and this is rarer. So n2 upon n1 is correct. Okay, that's nice. And what is this angle going to be? That's our theta, right? So sine theta upon sine alpha, cosine alpha. Sine alpha, okay, that is equal to n1, right? So sine theta is n1 cosine alpha. Now alpha is more than sine inverse of this thing. So like, what's the cosine of that? How does that behave? That's less than the corresponding cosine, right? So sine theta is less than n, and cosine of alpha is just a square root of 1 minus n. It should be n1. n2 squared upon n1 squared. It just means sine theta is less than square root of n1 squared minus n2 squared, right? That's the condition. So there we go, 20a. Okay, man, it's a shame. I mean, like in this amount of time, just did 20 questions. What is it? Fine, but that's it. So that's it for this video. I'll see you guys in the next video. Bye.